In this section, we're going to talk about how we can use derivatives of functions of two variables to find extreme values, to find maximums and minimums. And so the first thing I want to do is just remind you of some facts from, I guess it'd be Calc 1. In Calc 1, you probably learned that relative or local extremes can occur at critical points. And critical points were places where the derivative is 0. So that would be if you have a horizontal tangent line, you might have a max or a min. Or if you have a sharp point, a place where the derivative doesn't exist, that's a critical point, you might have a max or a min. Although not every single critical point is a max or a min, back in Calc 1 you had to check using either the first or the second derivative to see whether you have that max or min. And then you might have also learned that absolute or global extremes can occur at critical points, or they can occur at endpoints. So if you have a function on a closed interval, you might have your max or your min actually at an endpoint. So we're going to see that these ideas can be extended to functions of two variables. And so I'm going to start by giving you the extreme value theorem, which says if you have a continuous function of x and y defined over a closed region, then there has to be a place where the function takes on a minimum or a lowest value, and there has to be a place where the function takes on a maximum value. And we'll talk about how to do that a little bit later in this lesson. And then I'm also going to define critical points for functions of two variables. So we're going to say a critical point is a point x, y, such that either both partial derivatives, so f sub x and x sub y equal 0, so both partial derivatives equal 0, or at least one of those partial derivatives could not exist or be undefined, and then we also say it's a critical point. So let's just start by doing an example of finding critical points for a function of two variables. So I have the function f of xy equals 5 minus x minus 3 squared minus y plus 2 squared. So first thing I'm going to do is find my first partial derivatives. So if I take the derivative of this function with respect to x, let's see, only term with an x in it is the middle one. I'm going to use the chain rule, so I brought down the 2, and I get negative 2x minus 3 times 1. And then I'll do something similar to find my derivative with respect to y. Only term with a y in it is the last one. Using that chain rule, I get negative 2 y plus 2, and then times derivative of the inside, which is 1. So there's my partial derivatives. And then critical points would be places where both of these derivatives equal 0, or either one of them is undefined. And let's see, I don't have to worry about the derivatives not existing or being undefined because I don't have any denominators here. So I am just going to set both of them equal to 0 and try to solve. And so my f sub x, if I set that equal to 0, it's already factored. I get x equal 3. If I set the f sub y equals 0, y has to equal negative 2. So there's only one place where both of those derivatives equal 0, and that would be at the point 3, negative 2. And so I'm done with the problem. That's all they're asking for. I found my critical point. Now, it's possible that this critical point is a max. It's possible that it's a min. Or it could actually be neither of those things. In this particular case, because our function is, I guess, relatively simple, we can actually figure out what is happening at that point. So both of those squared quantities, the x minus 3 squared and the y plus 2 squared, are never going to be negative. If you square a value, you will never get a negative. Both of those quantities have to be bigger than or equal to 0. And so if we're taking in our function the number 5 and we're subtracting numbers that are always bigger than or equal to 0, that means our f of xy, our z value, or our function value, has to be less than or equal to 5. 5 is actually the largest value of z we could get because we're subtracting numbers from that 5. And then I guess we could argue if we plug that critical point 3, -2 into our function, we can actually see that the function value is 5 at the point 3, -2. And that is the largest value this function can take on. So this happens to be a maximum because our function values are always less than or equal to 5. So in this particular case, we actually have a maximum at our critical point. Frequently, though, you can't do this kind of reasoning to figure out if you have a max or a min. This really only worked because I had kind of a special function. So I am going to now give you something called the second partials test. And this is a way that we can check and see if a critical point is a maximum, a minimum, or a saddle point, which is actually neither of those things. And at the bottom of the screen, I do have some images. So minimum, maxima, and then the saddle point is not a max or a min. It's actually, if you kind of draw a trace in one direction, it looks like a min, but the trace in the other direction makes it look like a max. It ends up being neither a max or a min. So in our second partials test, we are going to compute a value called d, and I have it defined on the screen. So we're going to compute this value d by taking our second partial with respect to x times second partial with respect to y, and then subtracting our partial with respect to x and y squared. So that's what we're calling our quantity d. And then there's 4 different things that might happen. If the d value is positive, and our second partial with respect to x is positive, then we have a local min. This is analogous to the case where if you had a function that was concave up at a critical point, we said it was a min. And then let's see case 2, if our d value is positive but our second partial is negative, we have a maximum. It's kind of like our concave down situation. And then case 3, if d is negative, we have this saddle point. And then finally, if you get a d value of 0, unfortunately the test is inconclusive. That means it could be a max, it could be a min, or it could be a saddle point. All right, so let's do an example. Let's see if we can find all relative extrema and saddle points for the following function. So we've got the function f of xy equals x squared y minus 2x squared minus y cubed plus 3y plus 7. So I'm going to start by finding my partial with respect to x. So derivative of x squared y is 2xy, and then derivative of negative 2x squared is negative 4x. And nothing else has an x in it. And then partial with respect to y, let's see, first term, derivative of x squared y is just x squared. And then the next term with a y in it is the minus y cubed. That's minus 3y squared. Plus 3 has a derivative, plus 3y, I guess, has a derivative of 3. 7 is a constant. So then if I want to find my critical points, I have to set both of those partials equal to 0. So I'm going to set both of these partials equal to 0, and I'm going to see if I can solve. And so I think I'm going to start by focusing on my partial with respect to x, just because it looks a tiny bit easier to work with. It has only 2 terms in it. And in fact, I can factor this. There's a greatest common factor of 2x. So I can take a 2x out, and I'm left with a y minus 2. And then if I set both of those, or each of those factors equal to 0, I get x equals 0 or y equals 2. So my partial with respect to x will equal 0 if x is 0 or if y equals 2. So now let's use that information to figure out when will our partial with respect to y equal 0. So there's two situations that we have to think about. What happens when x is 0? So I'm just going to take 0, x equals 0, plug it into my partial with respect to y, and I get negative 3y squared plus 3 equals 0. We can solve that for y. 3y squared equals 3, so y squared is 1. That means y has to be 1 or negative 1. So when x is 0, if y is 1, or y is negative 1, we have a critical point. So that's two critical points, the point 0, 1, or the point 0, negative 1. Those are places where both of our partials equal 0. All right, what about when y equals 2? If I take y equals 2, plug it into my partial with respect to y, I'm left with the equation x squared becomes a minus 12 plus 3 equals 0. So x squared is 9. X is plus or minus 3. So that's two more critical points. X could be positive 3, y is 2. Or x could be negative 3, y is 2. So I've got 4 different critical points here. 4 different places where both of these partials are equal to 0. So my next step is to use this value d to determine whether I have a max, a min, or a saddle point. And so I'm going to start by just computing all of my second partials. So if I take my f sub x, find its derivative with respect to x, I get 2y minus 4. And then f sub y, derivative with respect to y is negative 6y. And then finally, my f sub xy, I took the derivative of f sub x with respect to y, I got 2x. Oh, I could have also taken my derivative with respect to y, my f sub y, found its derivative with respect to x. So technically, you could have found f sub yx. Those are always the same. Regardless, I get 2x. Okay, so I've got all my second partials written down. And then I like to organize the information in a table. So I'm going to create a table. I'm going to list all my critical points on the top. And then I'm going to take these critical points and plug them into my second partials, and then compute that value d to analyze what's happening. So I'll run through it with our first point. So when we have the point 0, 1, if I plug x equals 0, y equals 1 into my f sub xx, I end up getting 2 minus 4 or negative 2. And then if I take that same point and I plug it in my f sub yy, I get negative 6 times 1. That's negative 6. And then plug it into the f sub xy. So 2 times 0 is 0. And then I'm going to do that computation. I'm going to compute my d value by multiplying negative 2 times negative 6, and then subtracting 0 squared. That gives me positive 12. And then I'm going to run through, do the same computation for all 4 of these critical points. And so I just filled in the values on the table, but I'm doing the same thing. I'm plugging the numbers in to the second partials that I have listed. And then for the last row, I'm computing my d value by taking f sub xx times f sub yy and subtracting my f sub xy squared. And so hopefully I didn't make any arithmetic mistakes. I don't think I'm going to run through all of these. It really is just plugging numbers in, doing computations. And then finally, our second partials test says at the point 0, 1, our d value is positive. So anytime the d value is positive, you have either a max or a min. My f sub xx is negative. Negative is kind of like my concave down situation. So this is a max. So I have a local max at the point 0, 1. And then the rest of these points have negative d values. And anytime you have a negative d value, you actually have a saddle point. So the other 3 are saddle points. For completeness then, I went ahead and found the z values, the f of x, y values to write my answer. So if you take 0, 1 and you plug that into the function, you should get an output of 9. So I have a max at the point 0, 1, 9. And then my saddle points, I took x equals 0, y equals -1, plugged it into that original function. I got an output of 5. And then the same thing actually happened when I plugged in the 3 and the 2 and the -3 and the 2. And yeah, I got 5 for all those. So I have now circled on the screen my final answer. My max is at the point 0, 1, 9. And then I've got those 3 saddle points listed at the bottom of the screen. Let's do one more example. Same process, different function. Let's see if we can find all relative extrema and saddle points for the following function. So the first thing we have to do is find our critical points. So derivative with respect to x is just e to the x cosine y. And then derivative with respect to y becomes e to the x times negative sine y. So I wrote that as an negative e to the x sine y. Okay, so I'm going to set both of those equal to 0. So I'll start with the f sub x. E to the x cosine y, when does that equal 0? Well, e to the x is never going to equal 0. You can't take the log of 0. So we really just have to think about when does cosine y equal 0. I'll look at my unit circle. Cosine is the x coordinate. That's going to equal 0 when we have an angle or a y value of pi over 2. And then I guess we could add any multiple of pi. So pi over 2 plus k pi, I'm going to say. Okay, what about my partial with respect to y? Negative e to the x sine y equals 0. Same kind of reasoning. E to the x is never going to equal 0. When does sine of y equal 0? Well, that is right here. So that would be at an angle of 0 or pi, 2 pi, 3 pi. So I'll say k pi, any angle of k pi. So when are both of these derivatives equal to 0? Well, notice that I got completely different y values when I set my f sub x and my f sub y equal to 0. That means it's impossible for both of those partials to equal 0 at the same time. That is telling me there are no critical points. Right? Both partials will never be 0 at the same time. And so, therefore, since I don't have any critical points, there are no local extrema, and there's no saddle points for this function. The second thing I want to do in this video is talk about now how do we find our global or our absolute extrema. And so if we think back to functions of one variable, if I want to find an absolute max or min on a closed interval, I have to find my critical points, and then I check the output at the critical points and at the endpoints, because that absolute max, absolute min has to occur at one of those places. And so we're going to do something similar for our functions of two variables. If we have a differentiable function on a closed bounded region, we are going to find our critical points, and then we're going to find values of the function at our critical points inside that region, and then we also have to find the extreme values on the boundaries. And so that means it's going to involve finding some critical points on boundaries as well, and I'll explain that through an example. But the largest output will be our max and the smallest will be our min. So similar to what we did for functions of one variable, but of course a little bit more complicated. So let's take a look at an example. I want to find the absolute max and min of the function f of xy equals x squared minus 2xy plus 2y plus 3, and I have it defined on the region where x values are between 0 and 3, and the y values are between 0 and 2. So I have drawn on the screen the region we're talking about. The y values go from 0 to 2, the x values go from 0 to 3. So I'm talking about that rectangular region, that closed rectangular region. So the first thing I have to do is figure out, are there any critical points inside of this region? So to do that, I'm going to find my partial with respect to x. I got 2x minus 2y. And then I'm going to find my partial with respect to y. So I got negative 2x plus 2. I'm going to set both of those equal to 0. The simplest one to solve is my f sub y. If I set that equal to 0, I just get x equal 1. So f sub y equals 0 when x is 1. And then if I plug 1 into my f sub x, I can solve for y, and I get y equals 1. So both of these partials are equal to 0 only at the point 1, 1. So the point 1, 1 is a critical point, and I drew it inside that region, kind of to illustrate that that critical point is inside the region. If I got an answer like x equal 4, y equal 1, that's not inside my rectangle. I wouldn't consider it. Okay, so I have the critical point 1, 1. And then I'm going to go ahead and evaluate my function at that critical point. So if you take 1, 1, you plug it into the original function, I ended up getting 4. So the z value is 4 at that critical point inside my rectangle. We'll use that information later. Now the next thing I have to do is think about the boundaries. I have to try to find maximums and minimums along these boundaries. And so this particular image has a total of 4 boundaries. So the line y equals 0, I've colored it in purple, x equals 0 in yellow, the line y equals 2, and the line x equals 3. So those are the 4 different boundaries I'm going to analyze. And I'm going to try to find basically my critical points on my boundaries. And so let's start with the boundary y equals 0. So to analyze that boundary, I'm going to take y equals 0, and I'm going to plug that into the function given. So I'm actually going to compute f of x 0. So if I take this function given, and I replace all the y's with 0, this simplifies down to x squared plus 3. So this function along the boundary has the equation x squared plus 3. I'm going to find the derivative, set it equal to 0. So the derivative of x squared plus 3 is 2x, and that equals 0 at x equals 0. So this is telling me that along that boundary in purple, when x is 0, I should erase that, you can't see it. I drew a point in, I guess, blue on my screen. So I guess we're at the point 0, 0. That is a critical point along that boundary. Now, we do also need to check the other endpoint of that boundary. We have to check all our corner points, basically. So we're going to check this other endpoint that I kind of labeled on my image. I guess that would be the point 3, 0. All right, and then the yellow boundary, x equals 0, if I take my function and I replace all the x's with 0, I'm left with f of y equals 2y plus 3. I'm going to find the derivative of that. F prime would just be 2. 2 is never going to equal 0, so I don't have any critical points along that boundary x equals 0. But I do have to check the endpoints. So I added another dot there. I'm going to check both endpoints of that boundary x equals 0. And then y equals 2, that's the boundary in green. I'm going to replace all the y's with 2. This equation simplified down to x squared minus 4x plus 4 plus 3. So x squared minus 4x plus 7. The derivative of that would be 2x minus 4. Set it equal to 0. I get x equal 2. So along that boundary y equals 2, at x equal 2, we have a critical point. Let me try to circle it. It's right here. So that's, I guess the point 2, 2 is a critical point along that boundary. And then I'll have to check my endpoints. Okay, one more. X equal 3. I take my function. I replace all the x's with 3. I got 9 minus 6y plus 2y plus 3. That's simplified down to 12 minus 4y. Derivative of 12 minus 4y is negative 4. Negative 4 never equals 0. No critical points. But I have to check my endpoints. Oh, I already have those labeled. All right, so basically all of the blue dots on the image are places that I have to check. I had that one interior critical point located at 1, 1. And then the other 5 points are either endpoints of boundaries or critical points along boundaries. And so basically what I'm going to do is I'm going to check the function value, the z value, at all, I guess it's 6 of these points. So I'm going to organize my information in a table just to make it a little bit easier to see. So we've got the point, let's see, 0, 0, 3, 0, 0, 2, 3, 2. Those are my corner points. My interior critical point is 1, 1. And then that point, wait a minute, do I have these written down wrong? 2, 0, x equal, oh, it should be 2, 2. All right, let's see, that last point should be the point, yep, 2, 2, x is 2, y is 2. And so then I took each of these values, each of these points, I plugged them into my original equation to get my z values. That's the f of x, y. So I just plugged in the point 0, 0, 3, 0, 0, 2, 3, 2, 1, 1, and then that point 2, 2. And I have my outputs listed. The largest z value is 12. So I have a max at the point 3, 0, 12. And then the smallest I see is 3. That occurs at 2 different places. So I have minimums at the points 2, 2, 3 and 0, 0, 3. All right, let's do one more that's similar. Let's see if we can find the absolute extrema of the function f of xy equals y squared minus 2x squared plus 10 on the region bounded by y equals 4 and y equals x squared. So first thing I'm going to do is draw that region. horizontal line y equals 4, and that parabola y equals x squared. And then I'm going to see if I have any critical points inside that region. So I found my partial with respect to x. It is negative 4x. Partial with respect to y is 2y. I'm going to set both of those partials equal to 0. I got x equals 0, y equals 0. So I have a critical point at 0, 0. Okay, and then I do have to check my corner points. So that would be the points I have on the screen. That looks like the point 2, 4, and negative 2, 4 are my corner points. And then I'm also going to check and see if I have any critical points on my boundaries. So I'm going to start by considering my boundary y equals 4. So I'm going to take 4 and plug that in for y. I end up getting 16 minus 2x squared plus 10. So 26 minus 2x squared. That has a derivative of negative 4x, critical point of x equals 0. So on that boundary y equals 4, I have a critical point right here at x equals 0. So point 0, 4 is a point I have to check. And then again, I have to check those endpoints or corner points. My other boundary is the equation y equals x squared. So I'm going to take my function. I'm going to plug x squared in for y. So we're on that boundary y equals x squared. So I'm going to replace the y with x squared. And I end up with x squared squared. So x to the 4th minus 2x squared plus 10. Let's find our derivative. Derivative is 4x to the 3rd minus 4x. I'm going to set that equal to 0 and solve. So I can factor a 4x out. I'm left with x squared minus 1. So that has zeros at x equals 0. Okay. X equals 0 we already found as a critical point. And then x equal plus or minus 1. So again, we're on this boundary y equals x squared. At x equal 1 and x equal negative 1, those are critical points on this boundary. So I really need to draw the region we're looking at. It helps me see visually what are all the points I'm checking. So it looks like, once again, I have 6 points I have to check. 0, 0, 1, 1, negative 1, 1, and then 2, 4, negative 2, 4, 0, 4. Those are all the points I have to check. So that includes critical points along my boundaries. That would include any critical points in the interior. I don't actually have a critical point in the interior. And then my corner points or endpoints. So I'm going to take those 6 points. I'm going to plug those into the function given to figure out what my z values are. And I did that arithmetic. I just used a calculator, plugged those x's and y's into my function. Hopefully I didn't make any mistakes, but there's my z values. Largest z value is my max, so that was 26. So I have a max at 0, 4, 26. Smallest z value is my min. Looks like I have 2 of them. One at the point 119 and the other at negative 119. So it is kind of an involved process. The idea is we start by finding our critical points in the interior, and then we have to analyze each portion of the boundary. So we have to find critical points along that boundary, and we have to check those endpoints as well. All right, I've got one more example, I think. It's a long one. There we go. There's my last example. Finally, just like in Calc 1, you learn that why do we care about finding maxes and mins? Well, it helps us solve different types of applications. And so we can now use these processes to solve applications that involve maximums and minimums. So here's the problem I want to solve. I have a closed rectangular box with a fixed volume. So the box I'm looking at, three-dimensional volume or box, I'll just say its dimensions are x, y, and z, and its volume is 32 cubic feet. So x times y times z has to equal 32. The material for the sides is $1 per square foot, the bottom $3 per square foot, and the top is $5 per square foot. Let's see if we can find the dimensions of the least expensive box. So first of all, what are we actually trying to minimize? We're trying to minimize cost. And so I'm going to just write a cost equation. How would I find the cost of the material for this box? Well, the sides, there's 4 sides. One side has area x times z. And then there's another side with that exact same area that you can't see on the back of the box. Those sides have, let's see, a cost of $1 per square foot. So 1 times xz plus 1 times xz. And then we've got this side that's y by z. And then there's another one that you can't see over there. So 1 times yz plus 1 times yz. And then the bottom, which we can't really see down here, is x times y. That costs $3 per square foot. So 3 times xy. And then finally the top, which is up here, which is also x times y, is $5 per square foot. So putting together all those costs, adding up those costs times the area of the corresponding side, this equation simplifies down to 2xz plus 2yz plus 8xy. So there's my cost equation. I want to try to find the minimum value of this cost. I currently have a function of 3 variables, x, y, and z. The process that we learned works for functions of 2 variables. So let's see if we can use our constraint, our fixed volume here, to turn this into a function of 2 variables. So if the volume equals 32, xy times z equals 32, then z has to equal 32 divided by xy. And so I'm going to go ahead and I'm going to take 32 divided by xy, and I'm going to plug that in for z in my cost equation, and then try to simplify. And this will give me a cost function in terms of x and y. I'll have a function of 2 variables, and then I can apply the methods that we've learned in this video. Okay, so plugging that z value in and simplifying. So the first term, I canceled out x's. I got 64 over y. Second term, I canceled out y's. I got 64 over x. And then the last term is just 8xy. All right, I'm going to now find my critical points. So derivative with respect to x. Last 2 terms have x's in them. I get negative 64 over x squared plus 8y. And then derivative with respect to y. I get negative 64 over y squared plus 8x. So there's my partials with respect to x and y. I'm going to set both of those equal to 0. See if I can find critical points. So first of all, I'd like to point out that both of these partials happen to be undefined. The c sub x is undefined when x is 0. Can't divide by 0. C sub y is undefined when y is 0. Can't divide by 0. However, in the context of this problem, it just doesn't make sense to have a box with a width or a length of 0. You don't actually have a box. So those critical points aren't really in the domain of the problem. They just don't make sense. So I'm just going to try to figure out when do these critical point or these derivatives equal 0. So I'll start with my c sub x, set it equal to 0. So I just moved the 64 over x squared to the other side, and then 8y equals 64 over x squared. We can't really find a value for y yet. I mean, I could divide by 8, so this, I guess this simplified down to y equals 8 over x squared. So my c sub x equals 0 when y equals 8 over x squared. I'm going to take that value, I'm going to plug it in to my other partial derivative, see if we can actually make some progress. So negative 64 divided by y squared. So negative 64 over 8 over x squared squared plus 8x has to equal 0. Let's simplify and solve that. So negative 64 divided by 64 over x to the 4th, copy dot flip, that turns into a negative 64 times x to the 4th over 64. And then we still have the plus 8x. And then I'm going to cancel those 64s out, and I'm left with negative x to the 4th plus 8x equals 0. Here we go. Needed more room. Negative x to the 4th plus 8x equals 0. I can factor out an x. Oh, I'll factor out a negative x, actually. And then I'm left with an x to the 3rd minus 8. So either factor could equal 0. If x equals 0, well, we already talked about how that doesn't make sense. So let's not worry about that. What about x to the 3rd equals 8? That is true when x is 2. Okay, lots of algebra. So we just learned that both partial derivatives are equal to 0 when x equals 2. And then I have since erased it, but when we set that first partial with respect to x equal to 0, we ended up getting the equation y equals 8 over x squared. And so if x is 2, then y would be 8 over 2 squared. Oh, y is also 2. Okay, so both of my partials equal 0 when x is 2 and y is 2. That is my critical point. X equal 2, y equals 2. Finally, I should check, is this critical point a max or a min? After doing all that work and having only one critical point, I really hope it's a min, because that's what I'm trying to find. So I have written down on the screen, these are my second partials, and I'll just use my second partials test. So derivative of cx with respect to x should be 128 over x to the 3rd. Derivative of cy with respect to y is 128 over y to the 3rd. And then derivative of cx with respect to y is just 8. So I'm going to plug my critical point, which is x equal 2, y equals 2, into each of my second partials. Cxx was 16, cyy was 16. Oh, nothing to plug in for cxy, it's just 8. And then I can compute that d value by taking my cxx times cyy, so 16 times 16, minus cxy squared, minus 8 squared. I did that computation, I ended up getting a positive number. That's a good thing. When d is positive, you have either a max or a min. And then I checked the sign of cxx. It's 16. That's a positive number. That corresponds to my concave up situation. So this is a min, and and that's a good thing. That's what I was looking for. So least expensive box occurs when x is 2, y is 2, and then I guess for completeness we should give the z value as well. I have since erased it, but we said that if the volume is 32, then z would be 32 over xy. So z would be 32 over 2 times 2. That's 8. So the box should have dimensions 2 feet by 2 feet by 8 feet. And there is my final answer. That was my last example on this long video. As always, please let me know if there's anything that I can clear up from any of these examples.